So I study computational neuroscience, so I study the brain and AI, and I want to talk about something that I think about a lot, and that is what actually is a number. So I think I actually have an answer to the question, is maths invented or discovered? But you guys are gonna have to let me know in the comments what you think. So let's have a very deep conversation. Oh yeah, also, so in the end of this video, I'm going to talk about why I personally think about this question a lot as someone who studies the brain and AI. So yeah. Okay, so what is a number? There's a lot of answers to this question. I feel like the main answer is that numbers represent values or like kind of counting structures, like sets that are counting structures. But if we think about what actually, like fundamentally, what is a number? Like what actually is the truth of what a number represents outside of all of our human cognition and human constructs? What is a number? I was reading this book, it's on pure mathematics, and I was reading the section where he was talking about real numbers and rational numbers, and it made me realize what a number really is. And I also was talking to Claude about this, and Claude also made me realize what a number actually is. A number is basically a symbol that we invented in a base 10 system. Yeah. So it's actually kind of crazy that literally the foundation of mathematics is based on just the random chance that we were born with 10 fingers. So imagine if we were born with 12 fingers, all our numbers would be completely different. And would that actually change our theorems? I'm going to talk about that in this video, but it's just crazy because there's people who have dedicated their whole lives to studying things like numerology and vortex numbers. Like Nikola Tesla was literally obsessed with the numbers 369, which come up in vortex numbers. And vortex numbers is basically this idea, some people might call it pseudoscience, but it's basically this idea that when you keep doubling numbers, there's a pattern that comes up that it's kind of like a universal pattern, or it's like these numbers that come up everywhere, kind of like the Fibonacci sequence. So say you have like 1, 2, 4, 6, 4, 8, 16, 32, and when you add 6 plus 1, 7, and you add 3 plus 2 is 5. And there's a pattern that comes up within that. Well, they believed that this pattern was important, but then when you think about it, like the numbers themselves literally only exist because we have 10 fingers. Like that's literally it. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we have 10, 1 and 0. 11, 1 and 1. 12, 1 and 2. So is there actually something special about these numbers? There's non-human things that also represent numbers in their own special way based on their internal structure, and that is a computer. So computers represent numbers in base 2, which is binary, 0 and 1. So to a computer or a computer chip, the number 9 would be represented like this. And if anyone wants to know why computers or computer chips represent numbers in binary, it's because of physics. So long story short, basically the simplest, easiest way for us to kind of manipulate electrical circuits or to literally manipulate electrons in a system is to switch them on and off. Because it would be too complicated to start messing around with like magnitudes of the electronic field. Like it will start to get really noisy and you'd have to be able to deal with all the noise and all the messiness, and it'd just be too much. So the simplest thing to do is literally just switch it on and switch it off, which makes 1 and 0. So that's literally why computers represent numbers in binary. So the reason why I brought this up is because there's actually a very, very fundamental mathematical consequence of the fact that computers represent numbers in binary. And that is that certain numbers a computer literally cannot represent. So a number as simple as 0.1. A computer has no binary there is no binary representation of the number 0.1. So yeah, you're probably thinking, what numbers are there out there that we can't represent, that we have never seen or never experienced, that could be really important? Let's continue. So back to base 10. We're actually not the first humans that have represented numbers in base 10. There's an ancient civilization of humans that also represented numbers in base 10. That is the ancient Egyptians. 5,000 years ago, the ancient Egyptians would represent numbers from 1 to 10. So we represent numbers from 0 to 9. They represented numbers from 1 to 10. They also had different symbols for factors of 10. So 10, 100, 1,000, 10,000. So yeah, this number 10, is it important or is it just because we have 10 fingers? By the way, this is off topic, but it's funny that people always say that, like, how did the Egyptians build the pyramids? But if you think about it, the pyramids are triangles, and the ancient Egyptians were obsessed with triangles. Actually, every civilization of humans that were working on mathematics were obsessed with triangles, because triangles are actually really special shapes that encode this pattern that is. I'm making a video on it and it's going to be posted probably next week, but yeah, they could know everything about triangles, everything about shapes, everything about how to build triangles, how many bricks you would need for a certain height of triangle, how many, like, what height you would need to reach to have this type of structure. Like, they would know literally everything down to a T just from understanding triangles. So yeah, that's probably how they built the pyramids. They probably just like literally figured everything out before building it, so they knew exactly how much materials they need, how high they needed it to be, and everything. So it's probably how they did it. So yeah, the Egyptians were really, 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 really good mathematicians. The only difference between them and us is that they use maths to represent like real geometries, constructions, practical things, practical things in our three-dimensional reality. So for example, a square number is a square number, literally. So a square root is one part of the square, literally. For thousands of years, that is how mathematics was represented, as practical, real things. Until someone asked, what is the square root of a minus number? Or can there be a square root? When that question was finally asked, mathematicians wanted to understand what a square root of a minus number could even be. Because if you're thinking in our three-dimensional reality, or even just in terms of human cognition, the square root of a minus number literally doesn't make sense. Like, you can't have negative space. You can't have a square that has negative space. Even if you're thinking about bank accounts, like a bank account with a negative balance doesn't have negative money. It just owes money. So one of the most fundamental numbers that we use in mathematics basically all the time doesn't actually have a root in our physical reality or within our human cognition. It's literally a completely separate concept to how we would think about a normal number. So if that's true, if it's something as foundational as a negative number, let's see what happens when we go further down the rabbit hole. Okay, so now that we've created this concept of a negative number, mathematicians had to come up with different groups to represent different types of numbers. The ones we're going to talk about today are real numbers and imaginary numbers. There's also computable and incomputable numbers, which is actually crazy in itself, because an incomputable number means that there's no process to analyze that number. Like, there's no way that we can come up with an equation that can lead to that number, which means there's no way that we can ever probe this type of incomputable number. But let's talk about real numbers and imaginary numbers. So an imaginary number is literally a number that is the square root of a negative number. So what we've decided is that we're going to represent imaginary numbers as points on a 2D plot. So imaginary numbers basically have a geometric representation, or it's a geometric concept. And they're actually used to analyze and understand quantum mechanics and waves and angles and stuff like that because of their because of the geometric properties that we have given them. But remember that the number itself is just a symbol that we made up, which is why we can decide to give this specific group of numbers geometric properties. So what about real numbers? I feel like the term real number makes it sound safe and like stable, but within real numbers, there's rational numbers and irrational numbers. I think this is where it gets the most interesting because just the term imaginary numbers, we know that it's imaginary, that we've made it up. But the term real numbers, you would think that, okay, that must mean that there is some ground truth to it, that it is something that exists in some type of reality. But when you actually dig deep and try to understand what really a real number really is, you start to see reality just start to crumble, or I guess human cognition of reality starts to crumble. So a rational number is a number that can be represented as a ratio of two numbers. So rational ratio can be represented as a ratio of two numbers. And a ratio, it's not really another word for a fraction, but you can represent a ratio as a fraction. So every fraction can be represented as a decimal, right? So stay with me because we're actually going somewhere fascinating. So a fraction can be represented as a decimal, right? So what do you see in this decimal? In terms of its relation to a fraction, think about what base 10 actually does to a number. A decimal, specifically a terminating decimal, which is what a rational number is, it's literally just a fraction with a power of 10 at the bottom. That's the underlying mechanism of what our base 10 system is. It's literally a value, maybe a real value, something out there that is divided by a power of 10. So the number 3 is some value that is divided by a power of 10 or some power, some symbol, something. It's divided by something. So I guess the truth is, or the reality is, our number system, it's basically like a filter. So it takes something that might be real, something like a number that might be real, but then filters it into a way that I guess human cognition can comprehend. So, like a filter, it's not actually showing you what's actually there, it's showing you a human representation of something. So when we see a set with 20 elements, is that really a set with 20 elements, or is it a set that represents something of this convoluted idea of the number 20? So I guess this is a theory. I guess the theory is if a number is if our number system is some kind of filter, how or are we able to see past the filter? Like, are we able to see the reality, to discover something real, like to discover something that we haven't just invented? In 1931, a mathematician called Gödel proved that we can't. So Gödel's incompleteness theorem basically showed us the limits of mathematics, or in other words, he basically broke maths. So what he basically proved is that any system in whatever reality, if someone invents a system that can do basic arithmetic, that system has certain truths that it can't represent, because it's like, because you've created a system, there's things within that system that are going to be invented. Even if you're using the system to describe something else, there's things within that system that are always going to describe itself, which makes it illogical, which makes it impossibly incomplete, that it's impossible to have a system that it's impossible to create a system that doesn't refer to itself. So for example, let's say I say the number 1 is this thing. Then what is that thing? That thing is 1. then what is one? That thing. But then, so it's not that you can't describe a thing that you can see. It's not that the thing that you can clearly see doesn't exist. For example, 1 + 1 = 2. Like, we can clearly see that it makes sense logically. So this is fine when you're describing things that you can clearly see. But then when it comes to things that you can't see and you want to understand those things, you start to make things, you're going to start making ideas up that are representing itself, and you never really have a chance to understand what you're actually trying to understand. So yeah, if we can't use logic to prove our way into understanding phenomena like numbers, is there another way? Let's look at Euler's formula. Okay, so I'm still learning, so this is going to be a whole other video by itself. But Euler discovered this formula. He used the symbols that we invented to discover this formula. And this formula is basically rated the most beautiful equation in maths. What it basically does is explains phenomena that people have literally been studying for thousands of years. Like, literally the ancient Egyptians were trying to understand this phenomena that we found in triangles. From triangles, from symbols, we discovered this formula. So this formula or equation or identity, it kind of, I guess, proves or shows us that there is some truth to representing numbers in a geometric way. So there is some geometry to numbers, or at least there's a geometry to something that we represent as numbers. So I think we can say that there's a lot of different ways to represent a number. But then that brings up the same question: is maths invented or discovered? Like, what actually is a number? Because if I have a thing and I'm representing that thing with loads of different ideas, does that thing even exist? Like, for example, let's say I have this notebook. Imagine if someone else said this is a cup, and then someone else is saying this is a tiger, and I'm saying this is a notebook. Does this even exist? Like, what actually is this? Are people hallucinating, or is this even like, what is this? Am I making it up that it's a notebook? Like, that's how I feel about numbers, because it's like, if you can represent a number with all these different concepts, what is actually a number? Like, are we just using it as a placeholder for an idea that exists by itself, independent of numbers? And also, what other concepts are we not even aware of that can also be represented with numbers? I guess, like, we could ask, what do all these different representations have in common? So for example, what does the geometric representation have in common with the set theory representation, or the counting structure representation? We could ask what they have in common, but Gödel might say that there's just no way for us to really truly understand the foundation of maths. Like, what is the objective truth? Because I guess you could say it's beyond logic to understand the thing that this logical system was created to understand. And I've always wondered, what is beyond logic? I guess you could say like intuition, but is intuition stronger than logic? Not stronger, but like, is it more of a knowledge system, more of a truth system than logic? And also, is this really a limitation of logic, or is it a limitation of human cognition? If I'm to give you an answer right now, I think, well, first of all, I think that humans are limited. Like, human cognition is limited because literally we're not gods. Like, we're not all powerful, all knowing gods. So there's always going to be some limit. But I think that is what makes us, is supposed to make us more humans, and what is supposed to make us conscious beings, is that we can understand what we don't know. And I think the combination of logic and intuition is what makes us more stronger, what makes us more knowledgeable. So, for example, knowing that we represent numbers, well, we've invented this number representation system in base 10, we can then ask, Okay, so what would happen if there was another base system or other base systems? What would still be true and what would be false? And there's people that actually study that. So there's people that actually look at numbers and geometries and equations in different base systems to understand what is the truth and what is false. What they've discovered is that rational numbers are real. So the only thing about rational numbers that isn't real is the representation of them. So for example, the number the number 1/3 in our base system, there's no way to write it down. But in another base system, in base 3, 1/3 is literally 1/3. But then 1/10 in a base 10 system, 0.1. In a base 3 system would be recurring forever. So those numbers, rational numbers, are rational numbers. It's just that we can't write some of them down simply because of the way that we represent them in base 10. But it gets more complicated, or I guess the conclusion becomes more complicated. So prime numbers are always prime no matter what base system. And you'd think like, okay, that makes sense. That's cool. Prime numbers are prime numbers. But there is actually, I guess, a consequence of that result. So let's think about irrational numbers like the square root of 2. So the square root of 2, if you didn't know, it basically is just a string of numbers that keeps going and there's no pattern, so there's no way for us to know what it is in infinity. It's just an infinite digit of numbers that go on forever and there's no pattern that we can discern. And worse than that, any square root that is not a square number is always irrational in any base system. So that is kind of a weird result, and that kind of makes you think like, what's going on here? So there's no quantity anywhere in any base system. If you multiply that quantity with itself, produces 2 or 3 or 67, which means the irrationality of these numbers of the square root of 2 and the square root of 3 is a fundamental property of the number 2 itself. And you would think, okay, maybe there's something there, like maybe there's a truth to the square root of 2. But geometrically, I can basically show you the square root of 2 right here. So why does this happen? Why do these particular numbers start glitching when you try to find a square root? The reason is going to sound obvious, but it becomes profound when you actually think about the implications. So remember when I was talking about Gödel's incompleteness theorem and how any mathematical system will end up defining things in terms of itself. A square root is literally the property of a square. It's literally defined by itself. So a square root, a square number, it's literally a concept that we invented based on a question. What would happen if you had some geometrical shape that all its sides were the same length? What would the area of that shape be? And what does that tell us about numbers? So we created square numbers. We created square roots. But then we have functions that have squared numbers, cubic numbers, biquadratic numbers, which is numbers to the power of 4. So how do we have these, I guess, concepts of squaring and cubing in our equations, and they represent nonlinear changes, nonlinear functions, nonlinear growth? How do we do this when a majority of their roots are irrational? We have a few candidates. So it could be 1, numbers aren't real. It's just a human invention, which means that irrationality happens because we're trying to force these concepts onto things that aren't real. Or 2, numbers are real, but this idea of infinite precision of irrational numbers that go on forever, that idea doesn't exist. So those numbers genuinely just don't exist. I mean, we know that the universe, I guess, computes or exists on a fundamental level as discrete, not continuous. So a number with infinite precision or any type of length or any type of anything that has an infinite precision value doesn't exist. or can't exist in our universe or in the universe. So the square root of 2 just only exists in the human mind. Or 3, could it be that these geometric shapes that we've created aren't actually real and don't actually represent anything? Which would make sense because Einstein found that the geometry of our universe just doesn't allow for straight lines, which is why square roots only really exist for square numbers, because squares aren't real. So only numbers that have the invented concept properties that we've given them can be a square root. So the numbers are real, but the shapes aren't. Honestly, I don't even know which one it is. It could be all of them. It could be one of them. It could be, I don't know. But what I actually think about the question, is maths invented or discovered? I think it's both. They're actually real things that humans have discovered using mathematics. So even if the square root of 2 technically doesn't exist, we can use the approximation of this number, square root of 2, to discover things that do actually exist. It's only a problem when made up concepts don't align with something, a phenomena that exists in reality. For example, black holes. So we can square and cube and quadruple numbers and create symbols and concepts for things that help us understand real things. But then we get to a point, for example, with the singularity in a black hole, where we don't know how to interpret the result. So the answer to this equation that describes the singularity is infinity. But it's only infinity because when you do the equations, when you do the calculations, you end up with a division by 0, which is not allowed in our mathematical system. So really, the answer should be that it's a mathematical error. But how do we find out if within the center of a black hole, within the singularity, does reality really break down, or is it just our math that's breaking down? And how would we know which is which? So yeah, I guess my answer to this question, is maths invented or discovered? It's both. But we invent these mathematical systems, these axioms, these operations to understand things that actually exist. I guess to create approximations to things that actually exist. But then what happens when the maths breaks down? Do we interpret it as a breakdown of the mathematics, or do we interpret it as a breakdown of reality? So at the start of this video, I said I was going to talk about why I think about this a lot as someone who studies the brain and AI. And it's because I want to understand how exactly the brain represents numbers. Because the brain is basically, I don't want to say it's like a computer, but it does have computational processes. It has circuitry and wires, basically. It has circuitry that have binary representations, but then also it's a messy, biological, noisy, analog system that ions and liquids and chemicals are just flowing around all the time, creating electrical impulses all the time randomly. So within that type of structure, how do you create a mathematical structure or a logical structure from that? So remember when I said that computers represent numbers in base 2 in binary? The brain, well, neurons in the brain also have binary signals, which makes sense because, it's like the simplest way to represent or to manipulate electricity. But then at the same time, it still has to struggle with the messy biological, chemical reactions happening all the time that's creating electrical noise. But then how does it create cognition and perception and attention? Like, how does that happen in such a messy system, a messy analog system where you can't even digitally represent numbers, and yet the brain does it so well? So is it just binary, or is there something else that it does? Like, there's a lot of papers where we use electroencephalography, which is, it measures the electric field coming from the brain. But how do we know that the brain itself utilizes this electric field? Because as I said, like it's a messy, noisy environment where electrical signals are going off all the time, which has to generate an electric field, like just naturally. But how do we know that the brain utilizes that? And then also, how does the brain utilize that? So there was a paper that was published and it was completely separate, completely has nothing to do with computational neuroscience. It was like just a pure math paper. It was published like 4 months ago and or in April 2026. And it's called All Elementary Functions from a Single Operator. And basically what this person did was use a binary operator to compute literally every mathematical operation from this one single binary operator. And I think it has something to do with like the log or exponentials and logarithms. But as soon as I saw that, I was like, it's possible. Like, is this one way that the brain could be kind of computing and processing information using a single binary operator? So yeah, I'm still literally still learning, still doing research, but it's just stuff like this that just makes me like my brain just starts going and I'm just like, okay, now I need to get back to work. So yeah, I hope you guys enjoyed this video and yeah, let me know in the comments what you guys think as well. And I'll see you guys in the next video.